Hi, this is Ryan.
This is Oliver.
And this is Nathan.
Today, we're going to present our poster, VERTex, Variational Encoder Representations for Text. This is the final project for CS 236, autumn 2021. By way of background, current LNG practices are dominated by autoregressive models. However, these models are inefficient in text generation. In response, we propose a VAE for non-autoregressive text generation. What we do is we apply a VAE over text using BERT as the base of our encoder. Our goals with this are to produce more efficient sampling, but also to create a latent space, which allows us an avenue for more expressive text generation and generally more interpretability. With this, I'm going to pass it off to Oliver to describe our methods.
Yeah, our methods are described in figure 2. Figure 2 shows the VERTex architecture. Essentially, the architecture includes a VAE, which goes from words to words as well, with an autoencoding objective. Specifically, we take a sequence X, map it to the BERT embeddings, and then take the mean of each BERT embedding till we get a normal vector. Then we map it through two networks to get a mean and a standard deviation, or sorry, a variance. We use these to parameterize a normal distribution and then sample with the reparameterization trick. Finally, we put it through another deep neural network and output another sequence. Formally, if D is the data set of tuples H, the BERT embeddings, and X, the tokens, then our objective is shown in figure 3. Essentially, it's a modified VAE objective. You can see the autoencoding objective as well as the KL objective. Finally, we also experiment with the normalizing flows architecture. This involves not an end-to-end objective like the VERTex architecture, but rather we use flows to model the BERT embeddings within the latent space of BERT. Then to decode, we sample from the flow model. We map it to the BERT embeddings, and then we use the BERT LM head to predict actual words. Additionally, we also attempted a few larger models for larger sequences. Specifically, we attempted 2 different architectures, but did not get them working. Further directions could explore larger sequences or other generative models like GANs or score-based methods. Now I'll pass it on to Nathan to talk about experiments.
Yeah, so both training and evaluation was done on Wikitext 2. For the training, we'll just take a Wikitext sentence, chunk it up into sequences of tokens of our desired length. So we have n going from 2 to 4. And then, yeah, we will auto-encode those sequences using the methods we just covered. Evaluation of samples was done kind of qualitatively as well as quantitatively by sampling in the latent space and then decoding those using our fine-tuned decoder. So to share some examples of that, for n equals 2, you have bigrams like more freshman, electric California, and then as our sequence length increases, the fluency starts to drop a bit. Qualitatively, you can see that, a defined strength by enable is a little less fluent. And if we look at the numbers in table 2, you'll see that loss values go up, perplexity also goes up. And across all 3 sequence lengths, it's still quite a ways off from a real in the wild text, which is in that control row over there. So given these results, there are roughly 2 avenues, I guess, for future improvement. One is, the fluency of our existing methods. We're still working on that front, like Oliver mentioned, as well as increasing our desired sequence lengths. I think there are a lot of interesting ideas about how to do this. Yep. And
one thing I'd like to add is that in our table, we compare different n-grams. And our last one is something that's control. This may be a bit confusing, but this is actually just a representative text that was taken from the wiki text distribution, and we evaluated the perplexity and the perplexity per token on this sample.
Yeah.
The last thing we'd like to do is we'd like to acknowledge some of the help that we received along the way.
Yeah, this project wouldn't have been where it is now without help from our dear friend and mentor Ethan H. as well as our lovely CS236 CA Kelly. So thanks goes out to them, of course. All right, that is about it for our presentation. Thank you very much for listening.